Very
library. They're focused. Yeah, I'm not sure. Oh, yeah. There's a lot going on.
I'm going to do it next year. But I promise
I'm going to read
you.
that now. Did you just grab this last Friday? Yeah, but still. No, I think it's my people are. The difference that we
Hi everyone, welcome back. So I've got the quizzes with you. A lot of you who come to class have picked up your quizzes. If not, you can pick it up after class. This will probably be the last day I bring them to class. Otherwise, I'll have them in my office if you haven't gotten them. You can stop by during office hours. Or if you email the TAs ahead of time, otherwise they'll be in my office, not at their office hours. So we finished so very quick review of linear algebra on some Monday, and let's just see. You should mention homework 2 is due so next Monday. There've been a few questions, but it seems like there hasn't been anything quite as tricky as last time. Please visit the office hours. They're usually due on Wednesdays. This time they're due on some Monday. Remember, at 2:45 before class is the time it's due. And then the quiz there'll be a quiz in 1 week, again on the linear algebra, and then the linear regression stuff, which will start in this lecture. So we're going to talk about kind of the first kind of major block of data analysis techniques, where we're going to kind of find some more than one-dimensional structure of data. So linear regression. I'm probably guessing some fraction of you have already seen linear regression in some course. We're going to review it in this lecture, and then we'll build on that starting maybe the end of this lecture or over the next few, to show how to send this to multiple variables, how to do like polynomial regression, and then how to evaluate this with cross-validation. Okay, so who has used cross-validation before? Is this okay? So a few of you have used this before. Good. For others of you, this may be a newer concept. If you've seen linear regression before in, say, linear algebra or basic statistics class, you might be given like R squared value or something to try and measure how it is. Those are kind of like nice, I guess, but they're not really telling you about how well it's a more quantifiable way it's working with the data, and this is what cross-validation will do. This is kind of a really important paradigm of thinking about how important your data is, or how well it's working with the model. And it's we'll see this as part of this section on linear regression in the class, and it's kind of a newer way of thinking about evaluating your models. I mean, new, it's like a really old idea at this point, but it's different than how kind of fundamental statistics viewed it. And the change is because of we now have lots and lots of data. And we have like surplus data, and we can use that extra data to help evaluate our model. And prior to kind of 10, 20 years ago, it was not common to have all this extra data lying around that I could potentially use. So it's kind of changed the way we've approached modeling. And it will apply here, but it will apply in other parts of the course, and machine learning and data mining as well. Okay, so what's going on here? We're going to try and build a model to predict one value of data. And so we'll start with the simple case in this lecture and extend it. And we're going to have n so data points in 2 dimensions. Okay, they're kind of only going to be in 1 dimension. Kind of what dimensions they are, we'll kind of play with. Depends how you think about it. And this will be written as a set x, x, y, where x is uppercase and y is lowercase, and we'll see kind of why this is as we go. But it will be a set of these pairs where the first data point has an x1, has x value and a y value. The second data point has an x value and a y value. And then there's n of them, so it goes up to xn and so yn. And so we'll say that x is going to be the explanatory so variable, and y is going to be the dependent so variable. Okay, so we're going to use x to explain y. Y is going to depend. We think there's a model where the y value will depend on the x value. X will do the explaining of y. And so the reason that I'm going to write this as an uppercase x is it's very typical in a lot of applications here where this x part of it is going to become, this is going to gain more dimensions, but we'll keep y as just 1 dimension. There are ways to increase the dimension of y. We're not going to worry about those. We'll typically keep this. So that means I can put all these y values together, and it's going to be a vector. When I put the x values together, it's generally going to be a matrix. In this case, it's going to be an n by 1 matrix instead of an n by d matrix. D is equal to 1 here. But I'll just use this as uppercase x. Okay? Okay, and the goal here is, so the goal is to fit a line through the data y. And just to be clear, the line is going to take the form L, which is going to be y equals some function L of x, which because it's a line has to be ax plus b, where these values a and b are the unknown. So these are the unknown parameters which are defining what the line is. Okay, so the line is a function from the x value to the y value. Okay, and a and b are the unknown parameters. So I need to somehow figure out what are the values for a and b. If I know these 2 values, it defines this line. Okay, so instead of thinking over the space of lines, and you can write this as these kind of there are these kind of manifolds of the space of lines. We don't really think about that. We just need to think about these 2 scalar values now, a and b, right? Okay, and so a generally in this case is the slope of the line, and B is the intercept. Okay, so now let's, okay, so just to see an example, and I'll try and do an actual demo with this data later. But we have this example of, I think there are going to be, I have 10 different data points here in this example. So n equals 10, and I want to write another value down here. And then I have a y value here. Okay, so in this example, this height is x, and the weight is y. So I want to use the height to predict the weight. I want to find a line that goes through these. And in this two-dimensional case, it's nice we can actually draw a picture, and we can think of the x value, x going from about 100 up to 240. So this is the height. The height should go from about 60 up to about, in the data set I have here, about 70, 76. And the weight is the y coordinate. This goes from, this is in pounds, so 100 to 240 pounds. And it definitely makes sense to plot the points here. Okay, so, all right, so 66 is about 100, let's say 150, 200, and so something like this, and 250. So now 100 is, so 66 be about here, and about 160 is going to be here. 68 and 170, 60 is going to be 110, 70, 178, 65 is going to be about 155, 61, 120, 74 is going to be 223, 73 to 215, 75 to 235, and 67 is going to be 160 here. Okay, so this is the data I'm seeing, and again, the goal is to fit a line through here. I haven't exactly totally specified it yet, right? But I want to find some line. And so now this value here, which is about 110, would be about b, which is the intercept. And then the slope is kind of telling me something about the angle for every step, every pound I increase, or every inch I increase in the height, how many pounds do I increase in the weight? Right, so that's interpretation here. Okay, so hopefully you've seen values of the line before. Okay, okay, so I want to fit this line, but I want to do it. Now the important part about it is that the goal of this is to predict a new value here. So I've got this value 69 inches, so that's like 5'9", yeah.
So how do the intercept? This isn't the intercept of like 60. You're already shifted like 60 to the right.
Yeah.
The intercept ended up being like.
Right. So it's me down here someplace. So B is, you're right. So B will, I think, ends up being
15 or something.
Yeah. So we'll work it out later, but it'll be something small.
Okay.
Yeah. Good. Yeah, I didn't start at the plot zero. Good. Okay, so the really important thing is I'm going to get a new value here, 69 inches, which is like 5'9" or something. and I want to use this data to predict the weight. Okay? The important thing is I want to use this to predict what the weight is going to be. And so this kind of tells me something fundamental about how I want to model this. I'm going to assume that I know that the explanatory variable, and I kind of know this exactly. But I will not necessarily know on new data I get what the weight is going to be. So I want to predict this value. Okay, so I want to set up now a formula saying what does it mean for a line to be good? And in this case, it's going to correspond with these errors here. And these errors are specifically these vertical errors. I'm only measuring in the y-coordinate. Okay, I'm only measuring in the y-coordinate what the error is going on here. There are other things we'll see later in the semester where I want to measure something like the closest point on the line, which is not just the y-coordinate distance. I can get to a closer point in Euclidean distance on the line here, and when we talk about dimensional reduction, we'll do stuff like this, but we're going to measure just in the y distance. Okay, so what that means is that we're going to talk about these residuals. And so I'll say that an Ri for a data point I is going to be the yi value minus the predicted yi value, which is equal to the yi value times the model I have for L. Okay, I plug in the xi value, and this is going to make some prediction. Right, so if I have this fixed model, the red line for L, and I plug in an x value, I'm going to predict it's going to be right here on the line, but it's actually going to be different. And I measure the error in the value of this difference. This is called the residual. In this class, we'll take the absolute values, so they're always positive. Sometimes you want to kind of keep the sign around for various reasons, but so then I'd call it a signed residual. This is just the residual, and so I want these to be small, but I kind of want to combine this into a single expression that takes into account so all of the data, and so I'll write this as the sum of squared errors. I'll write this as SSE of the data and the line. So this will be the sum of squared errors, and this will be defined as I equals 1, the sum of the residuals squared, which is equal to the sum of the yi values minus what my model L is predicting based on the xi values, and this difference squared. I can take the absolute value, but then the square makes it always positive anyways. Okay, so I want to find the line which minimizes this error, measure it this way. Okay, so there are other ways of measuring the error. Instead, I could take the sum of the absolute values as the sum of the residuals instead, using the sum of the squared residuals. Okay, I could have measured the difference between the kind of the data point and the line, the closest distance, instead of just the distance in the y value. Okay, so let's talk about why we're using this error measure. Okay, so first let me talk about these residuals. Why are these important? there are two reasons there are two reasons why we want to base it on these residuals. The first one is that, as I mentioned, it's going to allow me to take a new x value, say just someone's height, and make a prediction on their weight. And this is what I want to emphasize, that predicting their weight, I assume that this is accurate. If I'm trying to match it to the closest point on the line, I'm essentially not assuming that the height value is accurate. This closest point here would instead have, it changes the height as well when I map it in this way. So I kind of want to fix the height, and I want to make a prediction on the weight. I'm given new data. I might as well assume that's correct. Make a prediction on the dependent variable. Okay, so one, this allows me to y. This allows me to make prediction on the dependent variable y. Okay, so my goal is to make a prediction. When I get new data to make a prediction, this is tailored towards that. The second thing about why to use these these residuals is that I can now have so it's okay to have different units here. Okay, I can use height to try and predict this weight. Okay, this is in pounds. This is in inches. This is going to be in pounds. I don't have to worry so much about mixing these units together. Basically, when I solve for A, whatever value I get for A, it's basically doing a conversion of the units inside of A. Right? So A is doing a conversion of the units here. If I were trying to map to the closest point on the line, if I change the notion of height from inches to feet, or to centimeters or to meters, it's going to change the definition of which point is closest. But in this case, I don't have to worry about that. I'm solving for A and this variable A, and this is actually doing the conversion inside of here. So I don't have to worry about it having different units. There's more advanced stuff in the book that we won't get to in this semester. If you put like so some form of like regularizer on the linear regression, and then you have to worry about the units. But if you don't have a regularizer, you don't have to worry about the units. Everything is fine, no problem. Okay. So these are kind of the two big things. Usually this is emphasized more, but this is kind of a hidden benefit of using this way of measuring error in linear regression. Okay, then the next question is why am I using sum of squared errors here? Okay, so this is kind of more like objective. This tells me these specific things that I can do, right? But this sum of squared errors is kind of, the sum of squared errors is a modeling choice. Okay, it's perfectly valid to say I want to minimize the sum of the residuals, not the squared residuals. Okay, that's a perfectly reasonable thing. It still satisfies these two properties. I'm still going to get a line. In this case, the line's going to look probably pretty similar. In other cases, it's going to look different. In particular, if there are outliers, minimizing the sum of the residual instead of some of the squared ones might work a little bit better. Okay? So why are we using the sum of the squared errors?
Yeah, it's closer to our idea of like Euclidean distance.
So yeah, so good. So I can think of these like residuals as I can stack these in so in some vector. Right? I can think of calculating residual for every data point, and what happens then is the sum of squared errors is equal to then the norm, the basic 2 norm that was the most common norm that we use. I put a 2 here just to be clear, right? It's the 2 norm squared. So I've squared this 2 norm. The fact that I minimize this instead of the square root of this, sometimes I write the root squared error or the root mean squared error. The square root is like a monotonic function. So they have this same minimum whether I take the square root or not. So I'm essentially minimizing the sum of the squared errors is the same as minimizing the 2 norm, which is the most common norm of the residuals. Okay, so if I write down as a residual vector, I want to make this vector small, and I use the 2 norm, then in our Euclidean distance kind of way of thinking about it, then this is kind of the obvious way of doing it. Okay, so this is kind of typically by default we should use the 2 norm, unless there's a good reason to do something otherwise. Sometimes there is, but if you don't have a good reason, you might as well use the 2 norm. Okay. Any other idea why this is by far and away the most common modeling choice?
Well, it kind of like looks familiar when we were talking about the Bayesian inference thing, but I don't really know how to make the connection, but like the equation, I think we really saw something similar.
Yeah, so there's the Bayesian perspective, okay, and so great. So you can derive this as the right thing to do under a Bayesian model, where you say that the yi values I observe are coming from a distribution that looks like the line of the xi values, right? This would give us now what we observe plus some error noise, and I assume the error. So I say that this is an equal here. This error, if this is a normal error with zero bias in it, so 0 bias and some standard deviation. So then this is a normal error, and I derive this through the whole kind of Bayesian framework. The maximum likelihood estimate is going to turn out to be this. And the calculation is similar to what we did earlier in the semester when we were talking about the Bayesian in 1 dimensions and just finding kind of a 1-dimensional normal error. Now we're saying it's generated according to this linear pattern, whichever we find, plus some unbiased normal error. If we set this as our model, then this turns out to be the right thing to estimate, to minimize in order to get the maximum likelihood estimate. So I'm not going to go through the calculations here, but you can believe me, if you assume this, then this is the right thing to do.
Going back to the sum of the squared errors, we're talking. Someone mentioned like the Euclidean being related to the Euclidean distance. Now, is there a way to visualize that in 2D? What that would be?
The right way to visualize it is in the n-dimensional space, and which is a little trickier to think about. But I want to think about this vector, this residual vector, which has n values, right? And so now there's some sort of ideal solution, and then there's but it has to fit on a line, right? So I can't achieve every point in this n-dimensional space. I can't have a line that kind of allows me to hit any point in the n-dimensional space. The lines are only defined by two parameters in an n-dimensional space. So what this means is it defines a two-dimensional manifold in the space. I think it's technically a manifold, it might have a cusp or something on it, but some two-dimensional subspace of n dimensions. And I want to find the closest, the point in that space of lines so that the L2 distance from the true data, the y vector, right, the y vector is n-dimensional as well, is going to be as close in the Euclidean sense to that as possible.
I think you can't really.
I don't know if that helped or not.
Well, I think I'm kind of like, you can't really visualize it in 2 dimensions because since the residuals aren't really in 2 dimensions, it's an n dimension, so you can't really.
Yeah. So this is useful. There's what's called like the normal equations, and we'll derive how to do this in higher dimensions, and it will turn out to be simple how to, a simple solution for it. But one way of kind of explaining why that works is what's called through the normal equations, and these operate in this n-dimensional space. There's some discussion of that in the book, which I was not planning on necessarily going through in class, but it involves some gradients and stuff we haven't talked about yet to go through it formally. But if you want to preview that, and then when you talk about adding regularizers onto this, you also want to think in this n-dimensional space. Well, you want to think about in a d dimension. That's a d-dimensional space again. But you kind of will again think of it's a projection into there. So again, you want to think about Euclidean distance, that things are parabolic because they're exactly the Euclidean distance in the n-dimensional space. So there's some more stuff in the book that we won't cover. The data mining class will talk a little bit more about these topics in the spring if you want. But again, it's hard to think about a little bit hard to think about in dimensions. But we have linear algebra, so we don't need to actually visualize them. Okay, good. So these are kind of the two modeling reasons which are kind of most commonly given. But probably the most powerful reason is that there's there's an algorithm. Okay. If I want to find, now I can formally state the goal is I'm given a data set, two-dimensional data set with x and y coordinates. I want to find the line which defined by solving for these two parameters that minimizes the sum of squared errors. There's a nice algorithm for this. Whereas if I change this error way of measuring error, the algorithms are not as clean and not as nice. I have to, like for the sum of the absolute values of the residuals, you need to use like linear programming, and there's a way to do it, but it's just not as clean, and it's not as common as what people use. Okay, so the cool thing here is there's going to actually be an algorithm. Okay, and in fact, it's going to extend to higher dimensions. Today, I'll write down what the algorithm is in the two-dimensional setting. And unlike some other algorithms we'll talk about in the semester, this one is basically going to have a closed form solution. Okay, so this will be in that I can write a couple lines of code and out will pop the algorithm. I don't need to kind of iteratively kind of improve on this. But actually, that's what we'll see how to do after we finish this section. In practice, they usually solve it in one of these iterative ways, and we'll come back to that. But for now, we don't need to do that. Okay, so I'm that's right. The goal is given x, y, which is going to be a subset of R2, right? So that means x is, in this case, going to be n by 1. I want to find L, which is a function of y equals ax plus b, to minimize the sum of squared errors of x, y, and L. So I actually am solving for these values A and B here. Okay, so I want to find the one which minimizes this cost.
Does it have a name, this algorithm?
So it's generally, is there a name? It's like, we'll see it on Monday, and it's like, it's just a couple of operations in linear algebra. I don't know if it has an actual name. I'll show you the version which doesn't use linear algebra yet, and then next week we'll say, now let's do it all with linear algebra, and it just generalizes, and you'll see that. And there's probably a name for it. I don't know what it is. Okay, so the algorithm. Okay, so I want to, and so it turns out in 2D it'll be both simpler but also more complicated, because there are some tricks we can do in higher dimensions, which I'll wait until next week to tell you. Okay, so the first step is going to be count the averages. And right, so I'm calculating the averages, and then I want to compute these vectors to calc the vectors x bar, which is going to be x1 minus x, uppercase vector, x2 minus x bar, xn minus x bar, and similar for y. Okay, so I'm giving these average vectors. Okay, and then I can solve for A is going to be written as the dot product of y bar, this is the vector, x bar, divided by the squared norm of x bar. So this is the solution for A up here. And B is then going to be y bar minus A x bar. Okay? So this turns out is the solution. I guess I did need linear algebra, but nothing too fancy. I could have written this up as, I could have just written out the definition of the dot products here. Okay. So I compute the averages. I have these vectors which have kind of removed the averages. Okay. Then I want to find the slope in this way, and then the intercept in this way here. Okay, so let me try and give some intuition of what's going on here. Back in my picture. Okay, so the first thing is, what is the average? Well, the average will be some point here. This will be x bar, y bar. Okay. I've done the coordinate-wise average of x and y. It turns out this generalizes as some good notion of average in higher dimensions, but I've taken the x average of all the x coordinates, the y coordinates. I can plot this as a point. Okay, and now I'm going to take the vector. Now I'm going to create these x bar and these y bar vectors in Rn. And so these are going to be instead these difference vectors here. Well, I'm going to create the x vector is going to be this value. Right, it's going to look like this, and then the y vector is going to be pointing in this direction here. Okay, and so it's first easiest to understand that we call b is equal to equal to y bar minus a x bar after we've solved for the slope of the line. So we've already solved for the slope of the line. What is this choice of b doing? Well, I basically solved this line, and I'm forcing this line so that it goes through this point. It turns out that the average point must be beyond this line in the minimum sum of squared solutions. So the solution for b is just forcing the intercept so that the line goes through the average. That's one way of interpreting it. A, right, if I write this as this this dot product, you can think of it this as a dot product, or as this times some cosine of theta, where theta is the angle in this n-dimensional space. Okay, and now these guys cancel. So it's going to be okay, so it's saying so the important thing to see what's going on here is that this is indeed canceling these units. Okay, so x starts out as being in the units of height, but I want it to be I want it to give me the equation is here. It's in the units of heights. I want it to be in the unit of weight. In order to do that, I need to multiply it by something which is in the units of weight over height, and that's what this is giving me. Some quantity in weight divided by some quantity in height, so it's converting the units properly. And as y gets bigger on average, then this coefficient will be bigger. So if I change the units from pounds to ounces, right, then this is going to increase, and the slope is going to increase in a way that's accordingly. This cosine theta is kind of saying, are these correlated or are these not correlated, right? Is the difference in this direction getting bigger as the x values getting bigger as the y values are getting bigger? If that's the case, then this angle will tend to be positive, and this coefficient will be positive. If it's the opposite way, then it'll give me a negative coefficient. Because this part only controls the scale, and this controls essentially the sign in some sense.
So when we take the averages of x and y, and if we were plotting it, it would always go through right through the center of that line. Is that right?
Yeah, that line will always be on it. Yeah.
So geometrically, where is theta on this diagram? Like where?
It's not on the diagram. It's in this n-dimensional space that there is n-dimensional residual vectors lie. It's an angle between these two vectors. right? Let me put this down. So theta equals the angle between x bar and y bar in n dimensional space. So I can't really see that. This part is I don't have a great geometric intuition for what's going on. Okay, so this is the algorithm for linear regression. The important thing is that it's finding this model, which is now more complex than these point models we were working with before. And if you use the sum of the squared errors solution, it's making a prediction on these y value only, and there's this closed form solution, this simple algorithm of how to find the optimal one. So from the data. So let me stop and just kind of show you this in Python, and then we can, if this is all clear, we'll keep going a little bit, and we'll start on extending this up to higher dimensions. Okay. That's one that's working. Okay, so what's going on here is that okay, so I'm importing stuff from NumPy so I can define these arrays. I showed you how to do that before, and this is me just loading up the arrays with the example I wrote on the board at the beginning. And now I'm going to plot this in. I have a new height, 69 inches. I want to predict the weight. I can do this. Great. So I can predict the weight, predict it at 183. Okay. And now I can do, let's add this guy back in. See it. And now I can plot this with the line as well. Okay, so now I've plotted with the line. How you do this is you generally set up this object called this lens space, which basically is going to between 60 and 76, which are the height values. I'm going to have 17 increments, and it's just going to connect these with little short line segments. There might be other ways of doing this, but this will generalize to curves as well. And so now this line, I can, for every value in here, I'm going to get, this line is actually going to be a vector. And then I'm going to do a plot of this as a line, and it's going to connect it by little line segments here. And I've made this in red as a line. And here's the line, and this red dot is on there, as we hoped. Okay, I can also do, let's say I want to do this prediction. Also, let's say it was 69, and I wanted to do this A times 69 plus B. And let's make this size 100 and C black. Okay, that's, so for the value 69, I'm predicting that the weight is going to be here. Yeah.
Shouldn't that be right on the line?
There might be some small issues in how it's been printed, but it should be right. I'm not sure why it doesn't look exactly on the line, but
I think we're doing like the scaling of the slides.
with the points, yeah, it could be that the point is actually up here and it plots it down. I'm not totally sure what's happening, but yeah, it should be exactly on the line.
Is there a way to quantify like how confident we are in our line of best fit in this instance?
Yeah, so we'll there are these kind of intrinsic, like these R-squared values, which we won't talk about. What I will talk about is cross-validation, and I will actually I will motivate that through for like a different reason, but yeah. So maybe we have time, so I can jump into a little bit this now. I think the right way of doing this is, okay, there are a few ways of trying to do it. If I only have 10 data points here, so that this is not like a large data set where I have a lot of extra ones, but what I would typically do is you would actually only build the model on a subset of the data. You randomly split your data into two parts, the testing part and the training part, and you build the model on the training part, and then you evaluate how well that works by calculating the residual on the leftover data, right? And then you get like an average residual or an average squared residual on the testing data, and this tells you on average how accurate are you, right? And if you have, and so the way to think about this is there's two concentrations of measures going on here. There's how well does your model reflect the actual data you have, and how well does your residual in the testing data represent the actual errors that you have. And so you want both of these training data and testing data to be large, and as you get more and more, the variance of both of these estimates are going down. You're getting a more accurate model with respect to the data you have as you get more and more training data. That doesn't mean that the errors are going to go to zero. Your data might be noisy. It says, how big is this? You kind of want to estimate how big is this variance here, essentially. And how accurate your estimate of this variance is going to go down with how big your testing set is. So if you have enough data that you can make both of these sets large, then you should do this cross-validation approach to evaluation.
This might kind of be a question, but if we pick enough data points, we would expect that for a height of 0, that the weight would be 0 as well. It would go right to the 0 point.
Well, okay, yeah, right. So you're getting back to this point of the offset being here was negative 300.
Yeah.
And then you're saying, should it actually be 0? So in some cases, that's a good thing to try and think about, whether that's accurate here. These are supposed to represent the heights of people, right? But these are probably not the heights of kids. They're probably, and you probably don't know anyone who is a height of 0 or a like weight of 0, right? Full-grown humans are probably roughly in this range. Probably there's a lower end of the spectrum, right? But in the data we have, this might be a reasonable spread of the data we have. And so what you're asking me to do is and we're not quite interpolating between these points, but we're making a prediction within the data, the region of data that we have. But you're actually asking to extrapolate, make a prediction in the region of data that we don't have, and say when the height is 0, should the weight also be 0? And that doesn't necessarily need to be true, right? So, and this is a question where cross-validation is actually very useful for this, because you're measuring it on the data from your population. And that's where it's important to be correct. Whereas maybe it'd be good to have the height of 0 means the weight of 0, but that's not so important actually. I'd rather do better on this data than to do better on some kind of conceptual reasoning, which, okay, it should be 0, 0. Right, does that make sense?
Yeah, so like, we almost want to check within the range of our height values, the x values, basically. We don't want to go outside of the x value range.
Right.
Less accurate.
Less accurate, observed data.
Yeah, and so okay, so and I'm hesitating. This question is, it's actually more complicated than it seems right now. As I mentioned, I'll try and give examples in low dimensions, but talk about high dimensions. In low dimensions, this is reasonable, right? I'm like, okay, I can give estimates between 60 and 76, and in fact, I've only plotted over this range. But now imagine that we have height and we have weight, and we're trying to predict the so like the shoe size or some other parameter. So now I say, okay, I'm using my explanatory variables are height between 60 and 76 and weight between 110 and 240. So should I be able to make a prediction anywhere for any data point in that range? Well, that may not be true. Is there anyone who has a height of 76 and a weight of 110? I'm not sure what to do with the data point here to make a prediction going this way. So capturing the region that the data lies in is much more harder to define in higher dimensions. And we're typically going to be in higher dimensions. Typically, the x-axis is actually going to be multidimensional, and the y-axis will always be one dimension. But this axis is going to be complex, and our data is going to occupy some subset of this space. Right? So trying to say where is the data accurate is kind of a tricky kind of question to ask, actually. But again, this is why this cross-validation to evaluate is useful, because we're using actual data points. So those are by nature kind of realistic values, right? So those give us unrealistic data. Then how realistic are the values we're actually predicting? Good. There are notions like of the convex hull of points in high dimensions, and maybe I think maybe we talked about this in later in the semester. But even those, there could be like gaps, right? And what do you do with gaps? There are ways you can say, look at the closest data points I have. What's the distance to the 5th closest data point? And if that is small, then maybe it's okay. But there are some weird parameter choices. Why is it the 5th closest instead of the closest or the 10th closest? And is it less than some distance? Again, when I'm again mixing, if this is the x domain, height and weight, I have to define a distance that mixes height and weight somehow. And that depends on the units in weird ways. So there are all sorts of issues with this, but cross-validation kind of skirts around these issues in some very, very nice, convenient way.
So when we were doing like math estimates with like our Bayesian methods, we were taking like a derivative to get the number at the end of it. But this all seems like very algebraic. So like, how do we get that being the solution?
Well, so if you remember, we could have solved it with a derivative, but I told you that the average or the weighted average gave you the right estimate. This is kind of an extension of the weighted average to fitting this this equation instead of a single value. So think of it that way. There is a proof in the book of why the higher dimensional version is accurate. So the geometry of the normal equations on, was it like page 88 or something like that. And so that actually rederives why this is the right solution using calculus again. So it's basically the same proof, but it's more complicated because you have this this linear set of linear equations you have to solve for the minimum of instead of a single scalar value. But it's basically it's the same process at work here. And that's why it connects to this Bayesian formulation with normal error. And if you derive the effect of the normal error in those equations, it turns out the negative log likelihood of a Gaussian is a squared residual. Cool, great. So you see, this is very easy inside Python. You know, there are many different commands, like this one that just allows you to do it automatically in one line. But I think it's important to kind of walk through and see how this is working, what's going on. And this is a parameter that we'll see what changing this means, if you can guess. But we'll see kind of constructively what's going on. So okay, well, let me turn this off and we can talk a little bit more. Okay, so let's talk about higher dimensions right now. And I'll introduce this, and if we need to, we can revisit it on Monday. But this is where linear algebra is going to be nice, not just for the notation, but it's actually going to give us kind of modeling power and power of algorithms as well. Okay. All right. So now our data set is again going to be here, where this is equal to this set. Okay, but in this case, we're going to instead say that xi is going to be an element of Rd, and yi is still going to be an R. Okay, so this is the more general form here, where, right, so now x is going to be, this is one person or object that we have measurements on. You have height, weight, income, shoe size, and so forth. And then we're going to bring, again, one value, kind of how many hairs they have on their head. I don't know what it is. I think I've got an example we can go through on Monday. Okay, so there are D explanatory variables. I want to make a prediction. So think of, say, I run a website we try and sell stuff. These are some attributes I have for each of the users for the website, and I want to predict how much money I will generate from this particular user over a year, right? And so I care if that person might come back to the website if I'm going to make more money from them as opposed to if I'm not going to predict to make money from them. Okay, but there could be a bunch of attributes that I'm keeping track of. Okay, so now my goal is going to be, now I want to predict a value based on some model of xi. Okay, so this is now kind of a more general model. right? And in the case with linear regression, this was a line, right? So before this was the model, and it was parameterized, saying it was A, B. Now I'm putting an alpha down here, and and it turns out this alpha will be useful here to think of as, and this model will take a nice form here. It's going to be alpha 0. J equals 1 up to D of alpha J xij. Okay, so I'm going to restrict my model, looks like this, where I've got a bunch of these values, and I'm going to put coefficients on them. So I wanted an extension notion of a line in higher dimensions. It turns out it's not a line. It's going to be a linear function. So for every value in the x domain, I'm going to lift this up, and I'm going to get one value in the y domain. So this is a function. So it's not giving me a line. It's giving me a d minus one dimensional subspace in the d plus one dimensional space, right? So this has d plus one dimensions, right? D from x and one from y. And in this space, right, so I'm going to get this plot where this is our d, this is r, and so my model is going to look something like, you know, this subspace here. This is m alpha. So now for any data point x, this is m alpha x. It's be some point up here, and in particular, it's going to give me some value here. So actually, probably the right m alpha is going to give me a single y value here. It's going to be this coordinate on the y-axis, right? So this point here is going to be x, which is in our d plus 1. So this could be a point in d plus 1 space. I assume I know the first d coordinates. I want to know the last coordinate. And what I care about is the value of the last coordinate here. And there's some linear function here which defines this. Yeah.
Sorry, I think you might have said that. I might have missed it. What does the alpha stand for?
Yeah, so alpha is going to be what parameterizes the model. Okay, so our model is going to be just defined by this vector. It's just going to be defined by this vector. Like with the line, I only needed these values a and b. Now I'm going to need d plus 1 values, right? This kind of serves the purpose of b, and these kind of serve the purpose of a, right? But now there are multiple values of a, and kind of I'm using alpha to kind of as a single vector to describe this, and so this parameter is here by this m alpha. Okay, just span this out. This is a alpha 0. Alpha 1 x I 1 plus alpha 2 x I 2. But so it turns out a convenient way of writing this, which is going to be really useful, is now going to be a dot product between alpha and 1 x. Okay, so I can think of creating this instead of thinking of x as a d-dimensional vector, I'm going to create a d plus 1-dimensional vector by just adding a first coordinate of 1 to all the data points. And then the model, the operation, this linear operation, is just a dot product between this alpha vector, which is d plus 1-dimensional, and this 1 and x coordinate here. Okay, so now I can actually think of these data points as actually being in d plus 1 dimensions instead, but they all lie kind of in the, or it's not really fit in the spot, but instead of worrying about the offset, I can add a coordinate 1 to all these points. What this does is it forces, now in this model, it has to, if this whole term is all zeros, then no matter what alpha is, the answer is going to be zeros, right? So this is going to go, this is in this d plus 1-dimensional space, this model will go through the origin. It will always go through the origin. But this first coordinate basically tells me the opposite. There's basically implicitly a 1 here.
Is this kind of like the same thing as the microperceptron where you include the basis, the bias into the...
Yeah, yeah. So as we see, many of the models in this class will actually just be dot products, including in the perceptron. Basically, we'll be able to write them down as dot products. Part of the reason they're all dot products in this class is I chose kind of the simplest version of a lot of different things you can do, and in the simplest version, they all look like dot products. There are more complicated things you can do. But for everything in regression we do in this, I guess in general, regression is all dot products. A lot of classifiers are dot products, like deep nets are not dot products. They're nested dot products instead. Doing a kernel SVM, if you've heard of that, that's a dot product, or it's an inner product, in some way as well. So we can, in the right space, you can think of it as a dot product, right? So everything is going to be dot products. This is not unusual. This is something beautiful that happens in all these things. Linear models are much easier to work with, and they turn out to be easy to work with. There are algorithms for them, and they're quite flexible, as we'll see.
Easy to compute.
Easy to compute, yeah. So this doing a dot product operation efficiently is like built into a lot of accelerators. Right? That's one of the core things that happens, and not just in machine learning, in scientific computing. This is the core operation as well. Okay, so this is, our models will now look like this instead of just a line. Okay, it's a little bit more complicated, but if d was equal to 1, then this isn't actually a sum. This is just one coefficient here and one value. So it's the same thing. I can just write this out as this linear function of all of the coordinates I have, right? So just a linear model. It gives me a d minus 1-dimensional or d-dimensional kind of hyperplane through here, which for every value x, I get a value y. Okay, so harder to kind of maybe conceptualize what's going on, but linear algebraically, it's just a dot product. Okay, and adding this 1 here is just going to simplify things. Now when I do the solution, I don't need to worry about solving for the offset. If I can solve for a in this way, after I've added this 1, then I don't need to do this step. Okay, it'll be implicitly solved in this first step here. Yeah.
This is just a notational question. Is it common to talk about vector concatenation with that, like, you make them a little, like, almost outer vector and like place one and then the other? Or is there like another way to do that?
Yes and yes. I think this is the most common way to write it. There also are other ways to do it. So you'll find, as long as you define your notation, you can, when you're trying to describe this to people, you can make up what's convenient, and you tend to get used to that when you're reading lots of these different algorithms. Sometimes to present it, I want to put this in some simpler form, or I want to make it more explicit, so I may change it for the purposes of explanation. This is probably common, but this isn't a totally common thing. This is this is one of the places it comes up. There, this is the main place it will come up in the class. So we'll stop here. We'll pick this up, and we'll see that you can solve this again, and this gives you is very powerful in what you can do by extending this.